Hello, our viewers. Previously, we have tried to see about magnetism. So we have tried to see some basic concepts as well. And at last, we have tried to see about the motion of charged particles in a mixed field. And the most common electrical components which use mixed or combined field are velocity selector, J.J. Thomson's apparatus, and the mass spectrometer. Therefore, at last we have tried to see that a velocity selector is a device which is used to determine the velocity of charged particles. In this case, for example, the charged particle is positive. Let it be a positive charged particle. And it's moving to the right with a speed or a velocity v, and immersed in a mixed field. The electric field is acting downward, and the magnetic field is acting into the page. The magnetic field is into the page. And the electric field, the positive plate is upward, and the negative plate is here, downward. So the field is acting downward, like this, from the positive plate to the negative plate. Therefore, the force exerted on the charged body due to magnetic field is upward, and the force exerted on this positively charged particle is acting downward. This is a force due to electric field, which is acting downward. Therefore, as the magnetic field is greater than, as the magnetic field is, which is acting upward, is greater than the electric field, the charged particle will tend to move upward. Whereas as the magnetic field, the force exerted by the charged particle is less than that of force exerted on the charged particle due to electric field, the charged particle will tend to move downward. But as these two are equal, the force exerted by the magnetic field on the charged particle is equal or the same as that of the electric field, the charged particle moves straightly, as we have seen here, like this. At that moment, both forces are equal. So mathematically, we can represent and find an expression like this. Actually, the combination of these two forces is known as Lorentz Force. But in this case, let's try to see that the two force is equal, and mathematically we can equate. Electric force can be given as electric field times charge, and the magnetic force is given as BVQ sine theta, where theta is 90 degrees. The velocity of the charged particle is perpendicular to the magnetic field, therefore theta is 90 degrees. Then you'll find an expression as this is 90, it's 1. So E times Q is equals to BVQ. So we can cancel out Q, the charge, and find an expression for the velocity. V is equals to E over B. Look at here. Electric field and magnetic field are directly controllable and measurable quantities. And the velocity V can be determined using such an expression, and is found on velocity selector. The other point here, the other electrical device which uses a combination or mixed field is J.J. Thomson's apparatus. And J.J. Thomson apparatus is sometimes known to be cathode ray tube in chemistry concepts. Therefore, J.J. means here Joseph John Thomson's apparatus, and it uses velocity selector in combination. And from work energy concept, it's possible to use work energy theorem. We know that work is equals to change of kinetic energy, meaning change of kinetic energy, the final kinetic energy minus the initial kinetic energy. And the final kinetic energy due to motion, half mv squared minus 1 over 2 mv initial squared. Okay? Initially, if the charged particle is at rest, it's possible to eliminate this if the initial velocity of the charged particle is at rest. Therefore, it's possible to have an expression, half mv squared is W, which is the electrical work done on the charged particle. In Unit 4, electrostatics, you have learned that it's possible to find electrical work done using a mathematical expression, charge and potential difference, or a voltage V. Or it's also possible to restate voltage as work or change of energy over charge Q. From this expression, we can rearrange and find an expression for the velocity. Charge Q times the voltage or potential difference V is equals to 1 over 2 mv squared. Look at here. Here we have a capital V and a small v. You should have to differentiate these two. Capital V is voltage or potential difference, whereas small v is the velocity of the charged particle. Therefore, from this, we can have an expression for the velocity V. So, what is the benefit of J.J. Thomson's apparatus? J.J. Thomson's apparatus. The use of J.J. Thomson's apparatus is to determine the charge per mass ratio of any given or unknown charged particles, the charge per mass ratio. For example, in the beginning, as electron is found, the charge of electron might not know, the mass of the electron might not known at that moment. But it's possible to find the charge per mass ratio using those controllable quantities. Mathematical expression is possible to find the charge per mass ratio. For example, Robert Millikan finds the charge of electron. At that moment, it's possible to determine the mass because it's already found the charge per mass ratio using this apparatus, using J.J. Thomson's apparatus. Therefore, from work energy concept, half mv squared qv, and it's possible to find the velocity from the velocity selector. We have already previously saw that. It's possible to find velocity V is equals to electric field over B. Therefore, when you resubstitute, you can find such an expression. In this case, it's possible to find an expression of charge per mass ratio as E squared over twice of V times the magnetic field B squared. All those quantities on the right side of the equal sign are all measurable and controllable. Therefore, it's possible to find the charge per mass ratio using J.J. Thomson's apparatus. Now let's proceed for the other concept. To determine or to discuss about the mass spectrometer, first let's try to see the motion of charged particles in a pure magnetic field, not mixed field. Rather, let's try to discuss the motion of charged particle in a pure magnetic field. Actually, it has circular paths. It might have a straight, or we'll try to see the different movement of charged particles in a uniform magnetic field. First, suppose we have a positive point charged particle, as obvious. Let's try to take a positively charged particle, moves in a uniform magnetic field. It might move parallel to the field, it might move perpendicular to the field, or it might move neither or perpendicular or parallel. It might have some angle. In this case, there are different paths in which it follows. There are different paths in which the charged particle follows. So what are those paths? First, let's take a positive point charge moving with a velocity v and immersed into a magnetic field which is acting into the page. As previously we have discussed that it's possible to find the direction of the magnetic force using right-hand rule. Therefore, in this case, it's a positive point charge and immersed into a uniform field which is acting into the page. Therefore, you should have to point your thumb to the direction of the velocity, and the magnetic field is into the page and the force is upward. Meaning, this charged particle is tending to move upward, gradually upward. Not directly upward, but it's gradually moving upward. Therefore, it's moving upward and reaches here. While it reaches here, again, the charged particle is moving with a velocity v upward, and the magnetic field is still acting into the page. So the direction of the force is towards the left, which means this charged particle is gradually moving to the left. It's moving to the left, and reaches here. At this point, again, the velocity of the charged particle is tending to move to the direction of to the left side. The magnetic field is still into the page, and the direction of the force is acting downward, meaning this charged particle is gradually moving downward. And now it reaches here. At this stage, again, the charged particle moving with that constant velocity is acting downward. but still the magnetic field is into the page. Now the force, your thumb points to the direction of the force, is acting to the right, which means the charged particle is tending to move to the right. Now look, what does it forms? It forms a circular path. So therefore, whenever a charged particle is moving and immersed into a uniform magnetic field, the charged particle tends to rotate and forms a circular path. In this case, it's moving anti-clockwise or counterclockwise. It's a positive point charge. If a negative point charge is immersed in the same field, it might move counterclockwise. In this case, it's possible to have a negative charge. It's immersed here. If you use right-hand rule, actually for negative charge, we have already said it's possible to use right-hand rule and invert it. So here we have the velocity. The magnetic field is still into the page, and the force is not upward. Since it is a negative charge, it's downward. So it's acting downwards and tends to rotate and forms clockwise path. Whatever the charge is, it might be positive or negative, they will form a circular path. They will form circular paths whenever the velocity is perpendicular to the magnetic field B. They will form circular paths when the charged particle is moving perpendicular to the magnetic field B. And we'll try to see about how to determine the radius of this circle and the period of this charged particle. The other point is, what if the charged particle is moving along a straight line or parallel to the field? What would happen to the charged particle? Well, let's try to see. Suppose you have a magnetic field which is acting to the right, like this. Let's take it to be like this. This is the magnetic field acting to the right. If we have a positive point charge and moving with a velocity v, either parallel to the field along the same direction, or the same charge might move opposite to the magnetic field. This is the velocity v, and it's moving opposite to the direction of magnetic field. Therefore, when we try to find the magnetic field, F is equals to BVQ sine theta. In this case, what is the magnitude and direction of the force? Well, there is no force exerted on this charged particle. Why? Because there is a magnetic field. Clearly, there might be a magnetic field. There is a velocity v. There is a charge q here. But the force is 0. Why? Because because of the angle between the velocity and the magnetic field. The angle as the magnetic field b and the velocity v are parallel, theta is 0. As the magnetic field B and the charged particle is moving opposite to the field, theta is 180. In either cases, sine 0 or sine 180 degree gives us 0. Therefore, there is no magnetic force exerted on a charged particle which are moving parallel to the field. In this case, what is the direction of the charged particle then? Well, the charged particle is moving along a straight line. There is no force to bend it in either direction, in any direction. So if a charged particle is moving along a straight line, and if a charged particle is parallel, moving perpendicular to the field, it has a circular path. So if a charged particle is moving perpendicular to a magnetic field, the force is maximum. The force is maximum and forms a circular path. It forms a circular path. And if a charged particle is moving parallel to the magnetic field, it has a straight line. The force in this case, in the above case, is maximum. In this case, it's minimum or 0. 0 when it is parallel. Now let me ask you one question. What would happen to the charged particle if it moves neither parallel nor perpendicular, but at some angle theta? Meaning, for example, here you have a magnetic field. This charged particle is not moving neither perpendicular to the field or parallel to the field, but at some angle theta from the magnetic field. Here we have a magnetic field, the magnetic field and the velocity of the charged particle is at some angle theta. The concept here is you have to decompose the velocity. The velocity can be decomposed horizontal and parallel. The parallel component of the velocity, tends to move the charged particles straightly. Whereas the perpendicular component, we have already said that as charged particles, the velocity of charged particle is perpendicular to the magnetic field, they will form a circular path. When it is parallel, they will move, the charged particle moves straight. When it's perpendicular, it forms circular. Again, at some angle theta, it has both components, the horizontal and the perpendicular component. So for the perpendicular component, it forms circular. For the parallel components, it forms, and the charged particles, it moves along a straight line. Therefore, the combination of these two forms what? It forms helical path, like this. It forms a circular path and try to move towards like this, in straight line. Therefore, it has both components. The circular, then what? It has a straight line. It tends to move this way. So let's try to see this. Like this. Look at here. The velocity v has both components, the perpendicular and parallel. The perpendicular makes it circular, and the parallel tends to move it along a straight line. Now let's try to see try to determine the mathematical expression and find radius r. In this case, for a perpendicular component, it forms a circular path, and that circular path has radius r. How do we determine the radius? Look at here. The force which tends to act towards the center is known as centripetal force. The net force which acts towards the center is known as centripetal force. So what is the net force exerted on this charged particle? The only force acting towards the center is due to the magnetic force, Fb. And that magnetic force, Fb, is given as bvq sine theta. Well, theta is 90 degrees in this case, therefore it's 1. Therefore, easily, the force, the net force acting towards the center due to the magnetic field is bvq, like this. And due to the centripetal force, we know that centripetal force is the net force acting towards the center, and mathematically given as mv squared over r. Therefore, equating these two equations, we can find an expression for the radius r as like this. So mv squared over r is the centripetal force. bvq is that centripetal force appears due to the magnetic field, the magnetic force. Therefore, equating these two, we can find the mathematical expression for the radius r. And r can be given as mass times velocity v over b times the charge q. Students, by the way, sometimes it's possible to find the other expression for radius r in terms of, let me ask you, what is the product of mass and velocity? I hope in grade 11 you have learned this as momentum. Momentum is the product of mass times velocity. Therefore, it's possible to find radius r as momentum p over bq. Okay, so momentum p is mass times velocity v. Let's proceed and try to determine the period. Okay, previously you have found radius r, and r is expressed as mv over bq. Now, let's try to determine the period. What does it mean by period? Period is the time required for one complete revolution, for one complete path. So as this charged particle is moving starting from here, let's take our reference point here, and reach here, the time it took is known to be period. And from your kinematics concept, you know that velocity or speed can be given as displacement over time t. So what is the total displacement for a complete path? Let's take a charged particle and reach here. It forms 360 degrees, or it forms one complete path, circular path, which is circumference. Therefore, S can be expressed as 2 pi r, circumference. And the time it took is known to be, period. So when you resubstitute, you can find an expression. So let's try to determine find the period t. So we have said that velocity v can be given as s over t, and the displacement, the total path, can be given as 2 pi r for one complete pass, or it might be possible to use r times theta. Theta is for one complete is 2 pi, and here you have r. So for one complete pass is 2 pi r, the circumference of a circular pass. And the time it took is known to be period, t, capital T. Therefore, from this velocity expression, 2 pi r is the displacement, and t is the time it took. So period t is 2 pi r over v. Then previously we have said that r, the radius of the circular path, can be given as mv over bq. Therefore, we can substitute here and find an expression for period as 2 pi. We can eliminate here v. We can cancel out v. 2 pi, we can find an expression for period as 2 pi m over bq. This is how we determine the period for a charged particle having a circular path. And the frequency is the inverse property of period. So frequency can be given as inverse of period. Inverse of period. When you invert this, you are trying to determine the frequency. You know that frequency is the measure of recurrence of something, redundant of something within a given unit time. So in how many number of circular paths it makes within a given second t. So it can be possible to determine frequency. And the other concept is it's also possible to find the angular velocity or angular frequency, sometimes known to be angular frequency, omega, small omega. So omega is equals to 2 pi f. So you can find an expression W is equals to bq over mass m. Students, I want you to try solve some problems and find on your textbooks and exercise on those equations. Now let's proceed on the other subtopics. Previously we have said that we have electrical components which use a mixed field. One is velocity selector, and the other is J.J. Thomson's apparatus. And here we have our third device, which is known to be the mass spectrometer. And the device which used to determine mass of charged particles, used to determine the mass of isotopes or chemicals. And it's possible to recombine velocity selector and a pure field. Here you have a pure magnetic field. B, pure magnetic field. And here we have a mixed field, which is a velocity selector. Using a velocity selector, it's possible to determine the tangential velocity v here. Previously, in velocity selector, it's possible to find the velocity v as electric field over b, E over b. At this case, after it passes through the velocity selector, it enters into a pure magnetic field. Previously, we have said that as a charged particle is moving with a velocity v perpendicular to the magnetic field here. Let's say the velocity of the charged particle is moving to the right. The magnetic field is acting into the page. Here we have it's acting into the page. So they are mutually perpendicular. The velocity is acting in this direction. The magnetic field is acting into the page. So they are perpendicular to one another. In this case, they will form a circular path. In this case, we just see only half or semicircular path. And here we have indicator. We have detector here. Detector. So as this charged particle moves and forms, kicks the detector. And it forms what? Here we can determine the diameter or the radius r. So we have a very nice mathematical expression and try to determine the mass of different isotopes. In this case, as the charged particle moves and forms radius of this, for example, one of the atom, the other atom might forms here, and the other atom might be here. So the detector reads the different locations of those charged particles, and they will form different radius. Due to that radius, it's possible to determine their mass. Look at here. We have a pure equation. Mass can be expressed using B squared, magnetic field B squared, the charge Q, twice of the voltage V, and R squared. You see? The mass depends on this value, on the radius. So different radius means different mass. All these are a given constant variables. Therefore, mass spectrometer is a very important device to determine the mass of different chemicals or isotopes. Let's proceed again. Students, now let's try to determine the force exerted on current carrying conductors. So far, we are trying to see the movement of charged particles in a uniform field, the force exerted on a single charged body, and so on. But now, let's try to see the magnetic force exerted on a current carrying conductor. By the way, this is the concept which develops electric motor. So previously we have said that if a charged particle, let's take a single charged particle here, a positive charged particle, as this charged particle is moving with a velocity v and immersed in magnetic field, in a uniform magnetic field, it's possible to have a force. The velocity v, the magnetic field into the page, and the force exerted on this single charged particle is upward, the force exerted here. But here you have a wire, a straight current carrying conductor or wire. Let's take only this segment. By the way, we are showing only half segment. It's possible to have here and here. We have a source. We have a source. Okay? So the charge carriers moves here and receive. So we can have different charged particles. They are moving with a velocity v in this direction, So the force exerted on each charged particle will totally lift this current carrying conductor upward. So let's say that this charged particle is moving a distance of s or a length of the wire L. Let's call it to be L. Look at here. We have a uniform magnetic field which is acting again into the page. By the way, it's possible to take it out of the page upward, downward. Okay? In this case, let's take the cross-section, the length of the wire, L. So on each charged particle, we have a force. And that net force tends to lift this current-carrying conductor upward. So now we are trying to see the magnitude and the direction of the force exerted on this current-carrying conductor. So previously, on a single charged particle, the force can be determined using this mathematical expression. F is equals to QV cross B for a single charged particle. What do you mean by the velocity V? And how do you determine velocity V? Well, velocity V is displacement over time t. Over time t. In this case, the displacement is the length of the wire. The length of the wire. So we can substitute here and find an expression as the length L over change in t or t. This is velocity. This is velocity. Here we have n number of charges. So n number of charges times the charge Q, the charge on the charge carriers, and they are all moving a displacement of L or length of L of the wire. So we can have a mathematical arrangement. Let's take it here. F is equals to n, the number of charge, Q over change in t. Change in t. And here we just left with L and B. LB. Let's take only the magnitude. At this case, n times Q over change in t. The rate of flow of charge per unit time t. Okay? Net flow of charge per unit time t is known as electric current I. We have discussed it in unit 5. Therefore, in this case, it's possible to find that electric current which flows through this wire times the length L cross magnetic field B. L can be termed as the magnitude of the length L and the displacement, the direction of the displacement. We can call it as L. Therefore, using this, it's possible to find the force exerted on a current-carrying conductor of length L immersed into a uniform magnetic field as I length L B. And here we have sine theta. Again, theta is the angle between the magnetic field and the length or the current, the direction of the current. For example, in this case, the direction of the current and the magnetic field are perpendicular because the direction of the current is in this direction is moving in this direction, and the magnetic field is acting into the page. They are perpendicular to one another. But it's possible to have different angles. So generally, we can find an expression. So F is equals to BIL. You might use BIL, or you can call it BIL for recalling. It means magnetic field, current I, and length L. As the current and the magnetic field are perpendicular, we can find the maximum force exerted on current carrying conductor. Let's take it here. So the maximum force exerted on current carrying conductor can be given as BIL. How do you determine the direction of the force? Again, the direction of the force is possibly determined using right-hand rule. So it's possible to use the direction of the current I, actually current with length L, vectorially I with L, length L. Okay, so the direction of the current I and the magnetic field. Where is the direction of the magnetic field? It's acting into the page. So we can have the force upward like this. It's possible to find the direction of the force. Now it's a time of activity. Students, I want you to solve those examples. Please take your time.